Section 814 is called industrial loads. And the primary part of this, I guess, just look at some different values related to industrial loads, wanting you to see the actual voltages that are encountered, the large currents, the other parameters that you have to deal with in such an environment. The other thing I want you to see is the information in there that says normally when we encounter a large motor or some other electrical machine in an industrial setting, we only have access to 3 terminals, maybe 4, counting the neutral. But the thing that we need to do is to make an assumption if we don't know the connection scheme of the device, and we're going to assume a Y connection in these situations. Now let's look at the reasons why we're doing this, and I will add a little bit to this in that there are ways that you can determine connection schemes via whether it's either Y or delta. You need access to some of the equipment specifications and access to some measure points. But overall, a lot of times we go into one of these situations and we don't actually know how it is connected on the incoming side or the outgoing side. Here's an example figure of power input to a factory. These are, accurate voltage levels. When we look at the figure A, we see a 2400 volt 3-phase line, 415 kVA apparent power per each line. We're also given with this problem the power factor here. So a lot of information going into this particular problem. We don't know how it's connected, so we are going to assume a Y connection. He tells us why we want to do that. He says that in a Y connection, the impedance per phase is understood to be the line to neutral impedance. The voltage per phase is the line voltage divided by the square root of 3. The current per phase is equal to the line current. For that reason, it's a little simpler to work. This assumption of a Y connection can be made not only for industrial loads, but for entire load centers, such as a factory that contains many motors, lamps, heaters, furnaces, so forth. We simply assume the load center is connected in Y and proceed with the usual calculations. So as you begin these problems and you run into other problems and it gives you general information, if you're not told that it's Y or delta, assume that it's Y. So for our particular problem, he says, I have a manufacturing plant that draws a total of 415 kVA from a 2400 volt line, 3-phase. If the power plant has a power factor of 87.5%, lagging, remember power factor always has a lagging or leading. It describes the relationship of the current to the voltage. So if the current is lagging, it's inductive. So he wants to know the impedance of the plant per phase, the phase angle between the line to neutral voltage and the line current, the complete phasor diagram for the plant. Yikes, a lot of stuff there, right? A lot of information, a lot of stuff to digest. He suggests that we begin to work this problem by determining what the particular branch voltage is. We can get that because we know E sub L is equal to the square root of 3 times the line to neutral voltage. Line to neutral voltage would be the line voltage divided by square root of 3. Okay, for our particular case, we've got 2400 volt line divided by square root of 3, and that comes out to be 1,386 volts from line to neutral. And he's showing us that here from line to neutral. So what we can do next is, when I do those long pauses, I'm actually coughing. But anyway, the current per branch is going to be the following. All right, give me a chance here. Let me write down some things, and I don't want to take up your time here, trying to be efficient with time. One thing I want to point out to you, and I just made the mistake, and I teach this every semester and work these same problems, and I still made the mistake. I want to show this to you. The first part of this, pretty straightforward, right? Getting the line to neutral voltage. Then what we're trying to do, but we have a voltage and we have the apparent power given to us. So when we know voltage and power, we can use a power formula to calculate the current, right? So first impulse, first thing I did, hopefully you're not doing this, but when I started to do this, I first wrote down apparent power is current times voltage. And of course that is true in a single phase circuit, right? But that's not what we're dealing with. And, quickly I caught myself, and I know that the formula for apparent power in a three-phase circuit is square root of 3 times the line voltage times the line current. Got to be careful with that. If that's the case, and we know that S is 415,000, and we know the square root of 3, we know that line voltage is 2,400, and what we're trying to find out, of course, is current. So current is going to be 415,000 divided by square root of 3 times 2,400. Hopefully you didn't make that same mistake that I did initially working that. If I crunch this out, 415,000 divided by 2,400 times square root of 3, I will get 100 amps as the current per branch. Be careful with that. Don't forget that. I see that a lot in this course, forgetting that this is three-phase system, and when we're given the apparent power like that, make sure that we recognize that as what it is, so we have to make sure that we include that square root of 3. So now we know the current. So what can we do here? What are we doing? I forgot what we were doing. Oh, we're trying to find the impedance. All right, so we got so much information. We can definitely find the impedance. If we know the voltage, so Z, impedance, Z, is equal to the voltage divided by the current. The voltage is 1386, and the current is 100 amps. Then dividing that into there, I will get approximately 13.9 ohms of impedance for here, and here, and here. The next thing he's asking is, what is the phase angle between the line to neutral voltage and the corresponding line current that is given to us? Well, for this problem, we're going to need our power factor, which we were given as 87.5%, or 0.875. The phase angle between the line current voltage, which is line current voltage, which is 1386, line to neutral voltage, 1386. And which one are we could pick any of these. Okay, so we'll pick this guy. And the corresponding line current of 100 amps, this guy, is going to be this formula, cosine of the angle equals the power factor equals 0.875. Inverse cosine of 0.875 is going to give us 29 degrees. And then the last thing he says is show this in terms of all of the voltage, the phase voltages. And we can definitely do that, right? We want to come 120 degrees here. And when we do that, we draw our voltage EBN. We put an angle of 29 degrees with the associated current. We come 120 degrees again. We have ECN. We come 29 degrees, and we have the current associated with it. Okay, and then of course from there to there would be another 120 degrees. So great problem, man. Just sort of takes on everything that we've done. The current lags behind the line to neutral voltage, making it an inductive environment. Current lags voltage, Eli, right? And then the complete diagram is, of course, all this. Really good problem, 810. I'll stop there, and I think we'll see what we need to do next.